In this example, we are going to design and simulate the use of a medical device, specifically a pressure sensor for the left ventricle. The premise here is we want to know the pressure in the left ventricle of the heart, but we don't want to do something as invasive as putting a sensor directly into it, so we want to be able to remotely monitor it. So we're going to put in a catheter or a small tube into the left ventricle that's going to siphon out some of the blood. The blood is going to go through the tube onto our pressure sensor, and then outside of the body, we're going to read the pressure sensor to get an idea of what the pressure inside the heart is. So a device like this would be useful for diagnosing different sorts of heart diseases or conditions, or for use of monitoring a patient during some sort of procedure in a hospital or in a doctor's office. But the problem we're going to see with the design of our device is because it needs to be small enough to go into the heart, and it has to be small enough that it's not going to be overly cumbersome or invasive. The small nature of it is going to lead to design problems that we need to overcome. So what we need to do is find a transfer function, because the pressure that we're sensing and the pressure that's actually in the left ventricle are not the same thing, as we're going to see in our diagram. So we're going to need to find the transfer function that will be the pressure in the sensor, I'll call that Ps, as we'll see in the diagram, to the pressure in the left ventricle. So it's our sensed pressure versus an input that is the actual pressure inside the body. So let's make a diagram of this fluid system, the fluid in this case being the blood. So the actual pressure is going to be the left ventricular pressure. So I'll call that PLV. And that is going to act as a voltage or as a pressure source. So in this case, the pumping of that left ventricle is going to be putting pressure on the fluid, the blood, and that's what we're actually measuring. So that's the pressure from the left ventricle. It's pushing the blood. The blood is going through the catheter, which is going to be a tube. Now, unlike those large-scale systems where the pipes were large in area, in diameter, we were ignoring the fluid inertia, we were ignoring the wall resistance. This is by design going to be small diameter catheter, small diameter tube, which means that we should be taking into account the wall resistance and the inertia of the fluid in the tube itself. It's going to be non-negligible. So I do want to model that. I'm going to have that wall resistance, R, that I'll be able to calculate, and I'll have that fluid inertia, L. So the R and the L are from the fluid traveling through the catheter. Then it's going to go into our pressure sensor. The pressure sensor is going to act like a tank. It's going to fill with the blood. We're going to be able to read the pressure in this tank, and then it's going to drain when the next pump is going. So it's going to take in here the filling of the tank, and that's going to come down here, and that's going to act as a ground at the bottom of that tank, and that's going to have some capacitance C. And then we can close our circuit down and reconnect it to the negative terminal of our left ventricle pump. And what we are interested in is what is the pressure across the capacitor. So basically, if we fill in the nodes here, this is going to be 0 since it's at a ground. We are going to have what we are going to call PS, which is also going to be, well, the pressure over here. So there's some pressure drop between PLV and PS as it goes through the resistor and the inductor, the wall resistance and the fluid inertia, and then it's going to drop down to 0 as we go across the sensor. So PS over PLV is what we want to find. So I've created the electrical analog circuit for this situation of the blood going from the heart into our pressure sensor, so we can use our diagram to find our desired transfer function. So the equation, actually we can do this in a single equation because we could just use the voltage divider rule. So that's going to tell us that PS over PLV is going to be equal to the impedance across PS, which will be 1 over C times S, over the impedance from PLV to 0. So we can add that together. These are all in series, R plus LS plus 1 over C times S. Now, as it's written, it's not in a good form because I have S's in the denominator of fractions in the numerator and the denominator. So I am going to take this and I'm going to multiply by CS over CS. So in the numerator, 1 over CS times CS is going to leave us with 1. RCS plus LCS squared plus 1 in the denominator when I distribute that CS through. And I'm going to rearrange this to have it in the standard form that we want. So 1 over the LCS squared plus RCS plus 1. That is the transfer function that we were looking for. That is the pressure at the sensor over the pressure at the left ventricle. That's the transfer function. We have this L, this C, and this R, but they're not defined quite yet because remember, this isn't actually an electrical system. This is a fluid system. So we're given some parameters about the catheter, at least initially, that the catheter is going to have some length L and some diameter to it, 5 millimeters. Again, the intention is it's a small diameter tube that we're inserting into the heart here. And the pressure sensor we are buying, this we're not going to be able to modify. It's really just the choice of catheter we use. The capacitor is going to have a capacitance of 3 times 10 to the negative 4th milliliters per millimeter of mercury. And we'll need to convert that into base units. We'll do that in the next step. And the fluid we're working with here is blood. So nominally, human blood is going to have a density of about 1,125 kilograms per cubic meter. And it will have this dynamic viscosity of 3.5 times 10 to the negative 3rd Newton seconds per meter squared. So where are these going to come into play? Well, remember, we have to make these analogs. So let's first look at, well, C is just given to us, so we don't need to do any calculations there. But L, the equivalent inductance, we are going through this round tube. So recall when we were deriving the equivalent inductance L is going to be rho L over A, right, of the tube. So that's of the catheter. So the fluid, that's rho from the blood, the length of the tube we're using, and instead of A, I'm going to do everything in terms of the diameter of the catheter. So area is going to be pi over 4 d to the second power, d squared. And the equivalent resistance, this is coming from that wall resistance. When we had a circular pipe or a circular tube with laminar flow, like we do now, or we're going to assume right now that we have laminar flow, the resistance is that 128 times mu L over pi d to the 4th power. So these are the equivalent values that we are going to be using to construct our transfer function. This is the L and the R, and again, the C is going to come from that pressure sensor. We're not going to have any choice over that. What we are going to be able to design is the catheter, so we can choose the L, we can choose the D, that is going to affect L and R, and we'll see how that comes into play. We have our transfer function now, so what do we actually want to do with it? We are going to take this into Simulink, and we are going to actually see how the input is going to affect the output as it goes through this transfer function. And we're going to do that with a combination of MATLAB and Simulink. In MATLAB now, I'm going to start by making a script file. And here I'm going to put in parameters of my system. So initially for my design and testing, I'm going to use that given information that I will use a catheter length of 3 meters. I'm going to do everything in base units here. A diameter of our tube or of our catheter of 5 millimeters, so 5 times 10 to the negative 3. And the capacitance from that pressure sensor, this is now converted into, again, base units, meters cubed per Pascal, instead of the given units, and that's going to be 2.25 times 10 to the negative 12th. And this is in units instead of the milliliters per millimeter of mercury. Now I'm going to put in the parameters for the fluid, again blood, looking up nominal levels here, the mu, the viscosity, the dynamic viscosity in Newton seconds per square meter, 3.5 times 10 to the negative 3, and its nominal density, 1125 kilograms per cubic meter. And now the calculations for our equivalent resistance and our equivalent inductance based on that circular catheter. And from how we derived it earlier, we can calculate for the blood properties and for the catheter properties what the resistance is going to be and what the inertia is going to be. So I am calculating it here in 15 and 16 because as I change my design of the catheter, as I changed D and L, that in turn is going to change the R and the L in my system and thus change my transfer function. And we'll see what those results are as we simulate this. But how do we actually do the simulation? Well, we're going to be doing it in Simulink. So I'm going to open up Simulink and I'm going to start with a new model. So I'll show some of the steps of building the model here. We're going to do more of this as we get into Unit 2 and 3, but we can get the start of an introduction to it now. I'm going to start by bringing in the left ventricular pressure from the time domain. So this is coming from actual data in this example. So we can see that the pressure is dwelling and that it's peaking, and this is going to keep repeating as I do the simulation. And if we see what this is coming in as, this is just for this specific example. This has a bunch of basically Y values of pressure values in Pascal versus a bunch of time values. So again, this is data that would be coming in from the clinic of actual left ventricular pressure that are measured inside the body. So what we want to do with this is we're going to put this is our input, into the transfer function that we're building. So what we can look at is if we look up transfer in this library browser, let me bring that up again, library browser, transfer, well I already did the search, I want to drag in transfer function. So this is where we can build the transfer function for this system. And we have to define our transfer function, and it's going to be similar to how we would do it in MATLAB itself when we use that TF tool, that TF function. So the numerator is 1, and the denominator here is going to be L times C, R times C, 1 as a vector. So this is that transfer function we've already derived, but I'm going to keep it in variable form. So what Simulink is going to do when I say L, C, and R, it is going to look into the MATLAB workspace for those variables, and it's going to use them. So as I change my diameter and my length of the catheter and then recalculate R and L, it will automatically be updating my Simulink model. So if I press OK, and I'll make it a little bit bigger so we can actually see what that looks like. Okay, so now we can see the actual transfer function. I'll zoom out a little bit. So what I want to do is I can click and drag from the output of left ventricular pressure to the input of my transfer function. So the input is left ventricular pressure. The output is going to be the sensed pressure, that P sub S. So I can double click and label this. This is PLV going in. And when we're ready for the output in a minute, we'll get to that. So right now it's giving me a hard time. It's red here because it doesn't know at the moment what L and C and R are. But when we run the MATLAB code, we'll see that this is going to turn not red because it has those variables defined. We want to get the output of our transfer function back into MATLAB so that we are going to be able to plot it and we can use it for some different analyses. So what we can do is we're going to do something called a vector concatenate, and we can look at it in our browser. Okay, here it is. So I'll drag this in and we'll see why we're doing this in a second. So I'm going to drag the output of this into the bottom here of the vector concatenate. And if I double click this, we can see how many inputs we want into the concatenate, and it'll come together in a second why I have 2 here. So this, double clicking, this is my PS. Now how do we actually get this into MATLAB so that we can operate on it? We need to put it into the workspace. So I'm going to look up workspace, and we want this toWorkspace function here. And then I'm going to connect these with the wire or with the arrow. And I can give this a name. So it is going to be called SimOut. Whatever I name it here is what it's going to be named in MATLAB when we run our transfer function or when we run our Simulink in general. So I'll call it SimOut. Now, what is it going to be doing? It's going to be sending this PS into this vector concatenate, and then the vector concatenate goes to the workspace. But I want not only the output, I want to be able to get the input as well. I want the left ventricular pressure also going into my workspace. So what I'm going to do is I'll control click on this branch, and I will send it to the top of this vector concatenate. So we'll see what happens here is the vector concatenate is taking these two different data streams, the PLV and the PS, and it's going to mash them together into something called SimOut. And then when I run it, SimOut is going to show up in my workspace and I will be able to work with it. So that's the very basics of making our Simulink model, and then we're going to be running it with MATLAB. So I'll make this a little bit bigger so we can see the basic structure of it. Now I'm going to use one that I've already built that looks just a tiny bit different, but it's doing the exact same thing. So again, I have my input, goes through my transfer function into the vector concatenate, and that's going to my workspace. So let me go back into MATLAB for a second. I'm going to run everything up to this point where I define my parameters. So I'm just pushing the F9, and now we see in the workspace, L and C and R are all defined. So now when I go into here, well, it's not quite. Okay, now it's been defined. And the other thing here is I want to simulate this for 6 seconds, 6 simulated seconds. So stop time up here I have as 6. I can run it for longer. We'll see how that affects the plots that we're getting. Okay, so what do we do with this? I've defined all my parameters already. Now to run my model through MATLAB, I'm going to use the sim command and then the name of the Simulink file. So this one, or the Simulink model, this one I have called the ME357L07 fluid level LV catheter. So pretty long, but that's the name of this file that I'm looking at now. So this says, all right, run it and then get the results. All right, let me go back and clear everything and do this in pieces. All right, so I run my parameters. Now I'm going to run my actual model with the sim command, and we'll see in the workspace when I run this. It runs it. It added 2 more variables to my workspace, this SimOut and also TOut. So let's see what those are. SimOut, that is again coming from this block here, this 2 workspace block. It took this concatenated vector, which is my input and my output from the transfer function, and it's saving it into SimOut. So let's look at the properties of SimOut. The name, not too important except we know which column is which. Really what we care about here is the data, the 751 by 2. So to access that, this is a struct in MATLAB. A struct is basically a variable that holds other variables. So it can hold vectors, scalars, it can hold functions. In this case, SimOut is holding, in particular, something called data. So I'm going to type, if I look at simout.data, this is showing me 2 columns of data. And what are they? Each column pertains to one of the things I put into that vector concatenate. The first column of data is the top input into my vector concatenate. And if I track that back, that is the LV pressure, the left ventricular pressure. The second data stream, or the second column of data, is the output from my transfer function. That is what I'm calling PS. That is the pressure that the sensor is measuring. So the order top to bottom of the vector concatenate corresponds left to right, the columns in simout.data. And TOut gives me all of the corresponding timestamps from the simulation. So I have the time corresponding to each of the measures, the left ventricular pressure and the sensed pressure. All of them correspond. This decided to make 251 times between 0 seconds and 6 seconds. So all of that is produced when I run sim. So let's look at the results from this particular simulation. So the first thing is I'm going to save a matrix called data, which is just simout.data. So we see that that's that 2-column matrix. And now I'm going to divide it because I know that the first column is what I'm calling PLV, the left ventricular pressure, and PS is the sensed pressure across that capacitor. That is the second column of data. And first, I'm just going to plot both of them at the same time. Now against that T out, the time from the simulation. So in black, I'm going to plot the left ventricular pressure, the actual pressure, and in red, the sensed pressure. And then put some other bells and whistles on here as I study it. So let me run everything up to that point. So this is what we get for our plot for that first design with a catheter length of 3 meters and a diameter of that opening of 5 millimeters. All right, so again, red, that's the actual left ventricular pressure that was given, that's the source, and red is what we're reading across our sensor. And we see that there is not necessarily as much agreement as we would like. So in the sensor, we're getting a much higher peak pressure reading than we actually have in the left ventricle. So we're reading a pressure max of about 225 pascals, let's say, 230 on that second one, whereas the actual peak, if I can hit it here, is only about 177 pascals. So we are reading too high from what the actual left ventricular pressure is. So if we're trying to monitor a condition or monitor a patient during an intervention or a surgery, well, we're reading higher than the actual pressure is in the left ventricle. So that's a problem. The other definite problem we have here is what we can call this ringing. So our reading is pretty spot on as we go up in the pressure spike, but then our pressure reading is ringing. We have these multiple peaks, whereas the actual left ventricular pressure just has this single peak and then comes back down, has a single peak, comes back down, and we're reading multiple. And then the same or similar problem comes after that pressure drops back down to 0 in the left ventricle. Our reading is ringing. We're seeing these oscillations here from the sensor that are not actually there in the left ventricle. So as far as a medical device for sensing the left ventricular pressure, right now, probably this one's not doing a very good job. We're overestimating or over-calculating what the actual pressure is, and we're experiencing these oscillations that are not actually there. If the red were the actual pressure of the left ventricle, this person would probably be in trouble because there shouldn't be these oscillations and we're reading a higher peak. So we might be reading this as something like an atrial fibrillation or something if we're seeing these oscillations, and we don't want to misread something as important as data coming from a medical device. So what's the problem here? Why is it not reading the same thing as the actual source pressure? Well, the source pressure is being put through this tube. We're adding this resistance, we're adding this inductance because of the wall resistance, because of the fluid inertia, and then it's also taking some time for the sensor to fill with the blood and then us to take the reading. So that's why we're not getting a one-to-one correspondence between actual pressure and the pressure that we are reading. Now, some things we might be able to do, thinking about going down here, how are we calculating this resistance and this inductance? Well, if R and L were smaller, if we have less resistance, less inductance, then it's more like we're going through this very smooth open tube, and it's not adding these extra delays and features into what we are reading. So to accomplish this, we can have our R be smaller if we have a diameter that's larger, because that makes the denominator larger. So if D is larger, R is going to get smaller. Also, if L is smaller, R is going to get smaller. So a shorter catheter and a wider catheter, a larger diameter open catheter, reduces R. And similarly for our inductance, a larger diameter increases the cross-sectional area, thus lowering the inductance. And also a shorter catheter, a smaller value of L, is going to reduce the inductance as well. So one of our design strategies could be, let's make R and L smaller, and hopefully that will make our readings better by reducing that equivalent resistance, reducing that equivalent inductance. So for second design, now I will uncomment this. I am going to try a shorter catheter, so only 1 meter long, and I will make a larger diameter opening of 8 millimeters. Now, what we could do is if we had an extremely short catheter with a very wide opening, well, that would make R and L really small. But the problem is going to be that this has to fit into someone's left ventricle. And if we make a really enormous tube, we're going to have a giant hole in the heart in order to siphon off the blood. And if we made the length of the catheter really, really short, well, then we're going to be taking our readings really close to the person, and then this remote sensing is not going to be very remote anymore. So there are going to be some minimums and maximums we have on the L and the D that we can use for our catheter design. But let's see, shortening our initial design and opening it up a little bit, how that is going to influence and change what we see as far as the fidelity of our measurement. So I'll run it now with these second parameters. And we see here in the second design, this redesign, on the whole, I would say it looks better, at least, than what we had. The peak reading we're getting from the sensor is 190 pascals or so. So it is still higher than the around 175, 177 of the actual reading, but it is closer than the first design. And we're seeing that the oscillations, we still have them down here, we still have them up here, but they're not as pronounced as they were in the first design. So at least by those qualitative measures, it looks like this design is better than the first one. Let me again go back to the first one for a second. So comment that out and run it. First design, again, much bigger oscillations, much bigger peaks. Now for a quantitative assessment of the difference between the actual pressure and the sensed pressure, we can use what is called the RMS error, which what the RMS error is going to do is from the figure, it takes the Y value of our actual signal and the Y value of the sensed signal at every time step, and it's going to take their difference. So the further apart they are, the greater that difference is going to be. It's going to take each difference and square it. So across the entire time span, it's going to, for each one, square it, and then it's going to add them together. And then what we're going to do is take the square root of that and divide it by the number of samples we took. So that in a nutshell is what the RMS error is calculating. So it's basically what is the average difference between our sensed reading and the actual reading. So the bigger this number is, we can say in general that our sensed reading is more different than our actual left ventricular pressure. So doing that calculation, and I'll have a link for more description of this, we get that for the first design, the RMS error is 28.1 about. Now that number by itself doesn't mean much because that just in isolation, we can't say that is good or bad. Is 28.1 good or bad? We need to compare it really to a different design and see, does the RMS error go down or does it go up? So for different designs in the same realm, comparing RMS values does have some merit. So first design 28.1. Let me go back to the second design and see what its RMS error is when I run this. It's only 9.2. It's much lower than it was from the first design. And we can see qualitatively that the points of the sensed measurements are closer in this design than the first design to the actual left ventricular pressure. So we should expect that RMS error to go down. With redesigns, we should be able to get this closer and closer, what we're sensing, to what the actual pressure is. And again, we can be monitoring the RMS error as one metric of how good a job is this design doing to capture the fidelity, capture the true nature of the original signal.